Okay, this is the homework for Unit 3, Day 3. It is on concavity and the second derivative test. So the goal of the second derivative test is we are going to again do a sign chart, but really it's going to tell us if it is concave, if the original function is concave up or concave down. So here's an example of concave up, here's an example of concave down, and that also tells us if there is a maximum or a minimum at that possible point of inflection, okay? So what we want to do here, kind of scooch this up a little bit. Okay, so for this first example, it's dealing with trig. So again, we have an interval there. We are only asked in the directions to find the point or points of inflection as well as the intervals over which it's concave up or concave down. So it is not asking us about intervals of increasing and decreasing. And because it's not asking us about those, then I can just go ahead like right to the second derivative. So I'm going to take the first derivative. And then normally we could pause there and then we'd be able to, talk about increasing and decreasing. But since it's only asking about the concavity, I'm just going to take that first derivative and then I'm just going to take the derivative of that. Okay, the derivative of sine is cos. Cos is negative sine. And so that'll be a minus cosine there. Okay, so now I took the derivative, or the second derivative. And now I need to figure out where the second derivative equals 0 or where the second derivative does not exist. I don't need to worry about this not existing anywhere because it's sine and cos, so it's bounded. I'm not dividing by 0 or anything like that. But I can figure out where that equals 0. So figuring out why the second derivative, okay, equals 0. So if I set this thing equal to 0, so negative sine x minus cos x, if I set that equal to 0, basically, I can move one of those over. It doesn't really matter which one. So I'm just going to say that I conclude that negative sine x equals cosine of x. And you're like, well, I kind of get stuck there, right? Well, not exactly. Think of on your unit circle where are sine x and cos x the same, and then we'll just need to make sure that one of them is going to be negative. So if I go to a unit circle here, notice this unit circle isn't rationalized, so I'm going to use this one instead. So notice that your pi over 4s, your x value and y values are the same, aka sine and cos are the same, but we really want them to be the same, but one is negative. So that would be in quadrant 2 and also again in quadrant 4. So it's going to be the 7 pi over 4 and 3 pi over 4 is what we're going for. And so I'm going to say that x equals, that was 3 pi over 4, and also 7 pi over 4 is where that's true. Now these are possible, okay? It's not for sure. There are possible POIs. And really there are possible x values of inflection, but I'm just going to call them possible points of inflection. So from here, I do need to draw a sign chart. So I draw a sign chart. And this time I'm looking at the behavior of the derivative, the second derivative, and it is going to tell me the behavior about the function. I put my possible critical points on there, and 7 pi over 4. And again, this is bounded, so really instead of having arrows here, I should really have end marks because, I'm bounded by 0 and by 2 pi, so I shouldn't really have arrows there. And so I'm plugging in. So when I plug in something in between 0 and 3 pi over 2, I don't know, a good candidate might be a pi over 2. So I'm plugging that into the second derivative. So if you plug that into the second derivative, so pi over 2, sine of pi over 2 is 1, but it's going to be negative. So I've got a negative 1. And the cosine there is going to be a big old 0. So it's going to be negative, because negative 1 minus 0 is negative. Then plug in something between. So a good candidate in between there would be something like pi. So when I plug in pi, sine of pi is 0, cosine there is going to be a negative, but it's minus a negative, so that's a positive. And then when I plug in, I don't know, something like 11 pi over 6, or doesn't really matter, just anything in between there, I'm going to get, that's going to be a negative. Okay. So that tells me that since this is the second derivative is negative, that tells me it's concave down here. Tells me the original is going to be concave up there and concave down again between those. So my conclusion would be that F is concave up on the interval 3 pi over 4 to 7 pi over 4. And I can conclude that f is concave down. And then I'm going to have to do a union on these two because there's going to be two. From 0 to 3 pi over 4, union 7 pi over 4 to 0. Okay, so I can conclude where it's concave up and concave down. And since the concavity did switch, those are indeed points of inflection. So I have a point of inflection at 3 pi over 4 is 0. And again, that y value is obtained by taking this x value and plugging it into the original. Okay, and there. All right, and number 4, again, we're going to skip right to the second derivative because it's not asking about increasing or decreasing intervals. It's just asking me about concavity. So I take the first derivative, then I take the derivative of that. And my goal is to take that second derivative and set it equal to 0 or where it does not exist. But in this example, I don't need to worry about the derivative not existing. So all I need to do is set that equal to 0. So if I set this equal to 0, I end up getting x equals negative positive 2. So again, this is a possible, okay, x value of inflection. So it's a possible POI. To determine it if it's truly one, I have to do a sign chart. So my sign chart, again, I put the second derivative there, and it's going to tell me the behavior about the original. I only have one possible POI there, so I just put a 2. I plug in a number like 0 into the second derivative, and that'll give me a positive, because it'll be 0 plus 12 is positive. Plug in a number to the right like a 3, that'll be negative 18, plus 12 is going to be negative. So that tells me here it's concave up, and over here it'll be concave down. And so it is asking me that I can say that h is concave up on the interval negative infinity to 2, and h is concave down on the interval that'll be 2 to infinity. So I have that. So you could say you do indeed have a point of inflection at 2. So you could say POI at 2, comma, to get that y value, you would take this 2 and plug it in there. So you're going to have a negative 8, negative 8 plus 24 minus 5 gives you 11. So we have that. Okay. Moving on to the back there of the worksheet, the second half. So it says find all relative extrema, use the second derivative test where applicable. So remember, one of the things we can use the second derivative test for is to also find the extrema. It basically says you take the first derivative, you set it equal to 0 to get those critical values. Then you take those critical values, so that's what's happening here. Take the first derivative, you get the critical values. You take those critical values and you plug them into the second derivative. So you kind of hold on to these, you go back and take the second derivative, and you plug those critical values back in. And when you plug those back in, you don't care so much about the actual number. You only care if the number is positive or negative. If it's negative, that means it's concave down, so you'll have a maximum. If when you plug in you get a positive, that means you're concave up, so you're also going to have a minimum there. Okay, so for number 5, what I did is I took the first derivative and I set it equal to 0. So by factoring, you can go ahead and get those critical values. Then I took the second derivative, so I took the derivative of this here. And then I need to take these critical values and plug them into the second derivative. So when I plug those into the second derivative, when I plug in 4, that's going to give me a positive 6, right? So that, what I really care about is that it's positive. So that means that it's concave up. And because it's concave up, that means that there's going to be a minimum at 4. So that we could say that there is a minimum at x equals 4. Then when you plug in a negative 2, so when you plug in a negative 2 into the second derivative, that'll be a negative 4 minus 2 is going to give you a negative 6. Again, I don't care about the 6 so much. I really care that it is negative. So that means I'm going to be concave down, which implies that there will be a maximum at x equals -2. So we have that there. Okay, in the next one, we are trying to figure out about the graph of the continuous function is given below. Now notice they give me the graph of the derivative, and they are asking me about questions about the original. Okay, so here it says find all the values of x on this interval. Notice that -6 and 3 are not included in there, for which f has a horizontal tangent line. So you should know that horizontal tangent line, well, horizontal tangent line means that your derivative equals 0. That's what that means. So this occurs when the derivative equals 0. Well, looking at the graph, where does that occur? Well, here the derivative equals 0 right here, here, and here, right? And so which of those are we going to steal? We're going to use -2 and 2. Why aren't we using -6? Because it's not included. So I would say that there is a horizontal tangent line at x equals -2 and x equals +2. And then it asks you furthermore, determine whether it has a relative max or min or neither at these values. Well, what you need to know is that we're really concerned about whether the derivative is going from positive to negative. That's when you get max and mins, or when you go from positive to negative or negative to positive. Okay, so to determine if you have a relative max or min at -2, you're concerned if the derivative goes from positive to negative. Well, if you look at -2, your derivative is positive and then positive. So there's no relative max or min at -2. So I'll just say at x equals -2, the derivative goes from positive to positive. So no max or min. Okay, so I don't need to worry about that one. Now let's examine what's going on at x equals +2. Well, at x equals +2, the derivative goes from positive to negative. Okay, the derivative goes from positive to negative. So that tells you that there's going to be a maximum, because that implies that your original, right? Think about what a sign chart would be. If your derivative, right, if you were just kind of picturing a sign chart, if your derivative went from positive to negative, that would imply that your function is going from increasing to decreasing. So that tells you that f goes from increasing to decreasing, and if you go from increasing to decreasing, that means there is a relative maximum there. Perfect. Okay, and then the last part here, so find all values of x on the interval for it has a point of inflection. So point of inflection, that's going to occur when you go from concave down to concave up, or concave up to concave down to concave up, or vice versa. Or really when your derivative, okay, so a POI, when your derivative goes from increasing to decreasing, right? So where does that occur? Well, where does your derivative go from increasing to decreasing? Looks like right here. And here it goes from decreasing to increasing, so right there. And we have it increasing, decreasing at 0 as well, and then it's decreasing, decreasing there. So we are going to say that happens at -4, at -2, and at 0. And that is your homework for the day.